Hi students, good morning. Our today's point is linear simple harmonic motion. So write down the point linear simple harmonic harmonic motion. Linear simple harmonic motion, that is linear S.H.M, that is S.H.M, that is S.H.M. Write down this point, linear simple harmonic motion, that is S.H.M. And the question will be asked on this point is explain linear S.H.M. Explain linear S.H.M. Explain linear S.H.M. Hence define it. Hence define it. This question is also important, so denote it as VIMP point. Now, in order to understand linear S.H.M, let us consider an example of oscillations of a pendulum. Suppose that this is a pendulum. When it is pulled aside and released, then we know that this pendulum performs to and fro motion about the mean point, but by careful observation arises some questions in your mind, and these questions are: why the velocity of the bob goes on decreasing, and why the bob stops at the extreme point and then again moves towards the mean point, and why the bob does not stop towards at the mean point, it moves towards left. These are the question, and the answer of this question is the explanation of linear S.H.M. And in this case, we are not able to understand which force exerts on the bob and pulls it towards the mean position, and therefore we make an arrangement of a spring. So the consideration of our answer is our first point, in which we are going to consider a block. This type of block is placed on a plain horizontal surface and a spring is attached to it, and due to an arrangement of spring, we are going to understand why the block stops at the extreme point and why the velocity of the block is maximum at the mean point and why it moves to and fro. All these questions can be clearly explained. All the questions of these answers can be clearly explained, and it is an explanation of the linear S.H.M. So write down the consideration. Consider a block. Consider a block. Consider a block is attached consider a block is attached to the spring from a rigid support from rigid support to a spring from rigid support, and consider a block attached to the spring from rigid support is placed on a plane is placed on a plane horizontal frictionless surface and when a block is pulled aside and released, it performs oscillations. So write down, when a block is pulled aside and released then it performs oscillations. This is our consideration of this answer. Now we know that we have to show this consideration in the diagram, in which we have to show a block attached to the spring, and therefore for the diagram let us draw three horizontal lines. At equal space, and then three vertical dotted lines at same spacing. The three horizontal lines should be start at same vertical distance, and end also at. That means three horizontal lines should be of equal length. Now here draw the block at right extreme point, then at mean point. Same block is this. So and at the left extremity block is same. So show these three positions of the blocks. This is extreme position, mean position, and left extreme position. And here also draw a rigid support at the same vertical line to which this block is attached by means of a spring. This is a rigid support. Now here the spring is in compressed condition. So write down first compressed condition spring. Now count the number of coils: 1, 2, 3, 4, 5, 6, 7, 8. If there are 8, then here you must show 8 coils, 1, 2, 3, 4, 5, 6, 7 and 8. Now here also you must show 8 coils, 1, 2, 3, 4, 5, 6, 7 and 8. One, two, three, 4, 5, 6, 7 and 8. Now suppose that this is a figure A. So figure A, and it is a stretched spring. Stretched spring. This is figure B. It is a normal spring, and this is a figure C, and it is relaxed. Sorry, this is normal or relaxed, and this is a compressed. This is a rigid support. Rigid support. Now denote this distance. Here the distance, suppose that is x, then this is the displacement here, x, but the force acting on the spring is here. Suppose that this is a extreme point, or don't denote it as extreme point. Here x is equal to 0 and f is also equal to 0 at the mean point. And at this extreme point, the displacement is also here. The displacement is here, and the force F is here. And at this point, V is equal to 0 and V is equal to V max. V is equal to V max, and at here V is equal to 0 and F is equal to F max. Or don't denote it here, only we are going to use this point. V is equal to V max and A minimum is equal to 0. Draw this figure A, B, C and D. Here the arrangement of this spring is for to understand why the block is moving towards the mean point and why it does not stop here and then it moves towards the mean point after left extremity. When the block moves towards right from the mean position, then spring gets stretched, and therefore restoring force acting on the block towards the mean point increases, so the velocity of the block decreases. Write down this first. When block moves towards right from when a block moves towards right from mean position, when a block moves towards right from mean position, full stop. Then spring get stretched, and and or full stop, then spring get stretched, full stop. Therefore restoring force restoring force acting on the block towards mean position increases so velocity of block decreases. So the velocity of the block decreases and at extreme point the velocity is 0. Or let us first explain this. Velocity of the block decreases. Therefore, the motion of the block, write down, and the motion of the block is expressed by equation, and the motion of the block is expressed by equation F is equal to minus kx, where k is force constant, or force per unit displacement, and x is displacement. The negative sign is due to force F and displacement x. The negative sign is due to force F and displacement x are oppositely directed. Here we explain, while moving the block towards the right from the mean point, the spring get stretched. Therefore, the restoring force acting on the block towards mean position increases, so its velocity decreases, and it is explained, and this motion is explained by this equation. And at the extreme point, write down, at extreme point restoring force is maximum. Restoring force is maximum at extreme point. Restoring force is maximum. So velocity is 0. That is, F is equal to F max and V is equal to 0. When the block stop at the right extreme point, the restoring force is maximum. So the block moves towards mean point with increasing velocity. Therefore, Therefore, block therefore block moves towards mean point. Therefore, block moves towards mean point with increasing velocity. With increasing velocity. And acceleration. And acceleration in this case. And acceleration in this case is given by write down, and acceleration in this case is given by A is equal to minus k divided by m into x. Therefore, the block moves towards, and acceleration in this case is given by, at the mean point, the block does not stop. At mean point, the block does not stop due to inertia. So, and write down, and at mean point, velocity is maximum. Velocity is maximum, that is v is equal to v max. But f is equal to 0 and x is equal to 0. When the block moves towards left from the mean position, then the spring get compressed, and it is the compressed position, and at the mean point it is a relaxed position. And when the spring get compressed, the restoring force acting on the block towards mean position again increases, so the velocity of the block decreases. So write down, when block moves towards left from mean position, when a block moves towards left from the mean position, then spring get compressed, then spring get compressed. Full stop. Therefore, a restoring force, acting on the block towards, therefore a restoring force acting on the block towards, therefore restoring force acting on the block towards mean point, increases. So velocity of the block decreases. So the velocity of the block decreases. And at extreme point, velocity, block stops, so its velocity is 0, and therefore, full stop, therefore block again moves towards extreme point. Block stops, so its velocity is 0. Therefore block moves again towards mean point with maximum, with increasing velocity, in this way block performs oscillations. In this way block performs oscillations. And in this case, the restoring force acting on the block is always directed towards the mean point. So write down, in this motion, a restoring force, acting on the block is always directed towards mean point. So this is a linear simple harmonic motion. So this is linear simple harmonic motion. So this is linear simple harmonic motion. And its definition is, so write down the definition, df raised to en From above discussion, we are able to define the linear S.H.M, and it is the linear simple harmonic motion is defined as the motion, the linear periodic motion of a body in which force or acceleration is always directed towards the mean position and magnitude of force or acceleration is directly proportional to the displacement of the body from the mean position. So write down this definition. The linear simple harmonic motion, linear simple harmonic motion is the linear simple harmonic motion is defined as the linear periodic motion, the linear periodic motion of a body, the linear periodic motion of a body in which force or acceleration, acting on a body is always directed towards mean position, and 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 magnitude of force or acceleration. Write down this definition. And magnitude of force or acceleration is directly proportional to the displacement from the mean position. And it is expressed as, that is, F is directly proportional to minus x, or acceleration is directly proportional to minus x. This is the mathematical expression of the definition of linear S.H.M.